Hey YouTube, in this video we're going to be discussing intracranial hypertension. Now intracranial hypertension, one of its effect is on cerebral perfusion, and we're going to talk about what cerebral perfusion is, and also the signs and symptoms and causes of intracranial hypertension. So let's get into it. So first of all, we want to know what intracranial hypertension is. Well, intracranial hypertension is a condition where the pressure inside the skull is elevated, which can lead to headaches, vision problems, and other neurological symptoms. Now, this number here, 7 to 15 millimeter mercury, this is the pressure. This is the intracranial pressure. So the normal range for intracranial pressure is 7 to 15 in adults. So intracranial pressure, basically the cranial vault, the skull, which is holding your brain, has a certain volume. And inside the skull, you might also know that there is a fluid quite similar to plasma, to blood plasma or tissue fluid, called the cerebrospinal fluid, or the CSF. And this fluid fills the cranial cavity alongside the brain. So this fluid, along with the brain, it fills the whole volume of the skull. So it exerts a certain pressure on it. And this pressure normally ranges from 7 to 15 millimeter mercury. Now, there are many causes that can increase this pressure, and this can lead to a lot of problems, like vision problems, because when you increase the pressure, you can start to compress nerves, and this can cause pain. This can cause damage to the nerves themselves and other things, like the cerebral perfusion, which we'll talk about in a bit. So next, we want to talk about the signs and symptoms. Now, intracranial hypertension there are many clues that can lead us to intracranial hypertension. The first one is obviously severe headache, also blurred vision. Let me show you some photos here. So blurred vision and headaches, vomiting, nausea, also alertlessness, and changes in behavior, like, for example, confusion, and it can also, in certain cases, cause seizures. Now, we won't be talking much about each of these signs and symptoms. These are just kind of general information for you to know. But what we'll be discussing next is the causes. Now, you can see here we have a few different causes. So we have a few different causes here: ischemia, cerebral edema, hydrocephalus or hydrocephalus, hemorrhages, and mass lesions. Now, I highlighted the ischemia and cerebral edema because these are kind of interconnected, and we'll be going into detail in these two. But as for the let's talk about some general info about each one. But we're gonna leave the ischemia for now. But for example, cerebral edema, as you can see here in this photo, it's basically the buildup of fluid in the parenchyma of the brain, and this can increase the intracranial pressure. Hydrocephalus, also same thing, but hydrocephalus is the buildup inside the ventricles, as you can see here. And mass lesions like tumors, abscesses, infarctions, all increase the volume of the cranial vault contents, which which leads to an increased intracranial pressure. And also, this right here, this is basically a hemorrhage in the cranial vault, and the buildup of blood, which is going to start to coagulate. It's going to make this. It's also going to increase the pressure. Okay, now for the fun part. This is my favorite part of the lecture. So we're going to be talking about cerebral perfusion, and we're going to be going into ischemia and edema together. So first of all, what is cerebral perfusion? It is the process of delivering oxygen-rich blood to the brain tissue, ensuring that the brain receives the necessary nutrients and oxygen needed for proper function. So this is basically it. The perfusion here means that you have arteries and arterioles bringing in oxygen-rich blood, and this blood is flowing to the brain. Now, we're going to be talking about what affects cerebral perfusion. So we have three things here. Yeah, let me just show this. So I covered up the terms. These are all acronyms, but I covered them up with some washi tape to make this a little bit interesting. So you can see each one here has a pressure unit. So these are all pressures. And this one seems pretty obvious, ICP, and we already mentioned this number before. So this one is intracranial pressure. So this is the normal range. Now for the MAP or MAP, it's 70 to 100 millimeter mercury. And if you're familiar with these numbers, you might be able to deduct which one this is. This is basically the mean arterial pressure, the pressure of blood in arteries. And then we have the third one here, which is calculated by this equation. We're going to be talking about that. This one is CPP, or cerebral perfusion pressure. So intracranial pressure, we already explained it. Mean arterial pressure is also pretty self-explanatory. Cerebral perfusion pressure means the pressure, the minimum pressure that is required for blood to flow into the brain and into the cranium. So this pressure is calculated by this equation. So just move this a little bit. So yeah, let me show this. Okay, so CPP equals MAP minus ICP. And why is that? Well, let's think of the pressure. The CPP is the pressure of required for blood to flow to the brain. So this means that there are mainly two factors affecting this pressure. This blood is flowing through arteries, so it's definitely affected by the mean arterial pressure, whatever that is, right? So this is the driving force of blood into the brain, the mean arterial pressure. But we also have a resisting force, which is the intracranial pressure. So the intracranial pressure resists the flow of arterial blood into the brain. And this is why the cerebral perfusion pressure is calculated as such. So as shown by these arrows here, these show the relationship of intracranial pressure with CCP and also mean arterial pressure with CCP. So if you increase the intracranial pressure, the CCP goes down because, as we said, the ICP is the resisting force. So it's the pressure is pushing on the arteries, it's slowing down the flow of blood. And likewise, if the mean arterial pressure is low, that will also decrease the CCP, because the net of this equation, if you increase the ICP, then the net is small. If you decrease the ICP, then it's larger. If you do the same with the MAP, it's an inverse relation, basically. So this is the cerebral perfusion pressure. Now let's talk about this is my favorite part of the video, which is this cycle. So we have a basic understanding of what cerebral perfusion pressure is and what cerebral perfusion is. Now let's talk about an example. So let's say in this case, you can see this represents one of the causes of increased intracranial pressure, hemorrhage. So there was a hemorrhage in the brain. There's a hemorrhage in the brain, and this blood is starting to fill up and coagulate and take up space. So it's increasing the ICP. Okay, so that makes sense. Now, as we just said, increasing the ICP, as shown here, will decrease the cerebral perfusion pressure. So in turn, decreasing the cerebral perfusion pressure will decrease the CBF. Now, what is the CBF? It's the cerebral blood flow. So CPP is the driving force for blood flow, for the cerebral blood flow. So if it decreases, also the blood flow will decrease. So if we have decreased blood flow, then we start to get ischemic. So as we talked about this before, one of the causes, it might not be a very direct cause, but it is a cause, and we're going to understand why ischemia is part of this cycle. So if we have a decrease in cerebral blood flow, this means the tissue, the brain tissue, is not getting enough oxygen. So it's starting to become ischemic. And then this can lead to hypoxia. And this will have two effects. Now, an ischemia, the hypoxia, will have a cytotoxic effect on the cells. So the cerebral cells, they have, we know they have sodium potassium pumps, and these pumps require energy. So if they're damaged, this means there won't be a regulation of ions, a proper regulation of ions inside and outside the cells. So this, alongside a disrupted blood-brain barrier, these two effects can lead to edema. So we call the first one the cytotoxic effect here. This is called a cytotoxic edema. So an increase in edema that is cytotoxic is called cytotoxic edema, but the one that is through a disrupted blood-brain barrier is called vasogenic edema. And so you can see here that this vicious cycle, we also mentioned that edema is a cause of increased pressure. So even if the initial cause was hemorrhage, this can lead to ischemia, and the ischemia is going to lead to edema, and then this cycle keeps continuing, and the pressure keeps increasing, and it's just this vicious cycle. So that's about it for this video. I hope you understand. I hope you benefit from this video. If you like it, please consider subscribing and liking the video, and I'll see you in the next one.